Right, okay, so in this video we're going to be working on the topic of bases, okay, and bases we're going to use the equivalent algorithm for part of this. So when we're dealing with bases, we're going to look at it in two parts, okay. Bases is the number system that we use, okay. So every number that we've seen is basically in base 10, okay, that's the base structure we use, okay. So units is 10 to the power 0, your tens column is 10 to the power 1, your hundreds column is 10 to the power 2, 10 squared gives you 100, that's the base structure we use, okay. So what we want to do though is know how to express base 10 numbers, or base 10 integers I should say, into other bases, okay. And other bases. Okay, so that's going to be the first part of this video. We're going to look at how we do it into other bases. Okay. So that's going to be the first part. And then the second part is going to be, if we start with a number on a different base, how do we get it into a base 10 again? Okay, which is like the normal number we use. Okay. So we're just going to go straight into an example. Okay, and I'll show you how it works in this case. So example 1, we're going to express the integer 235. Okay. And we're going to write down as a wee subscript, that's base 10 we're talking about, which is like a normal base structure for us. Okay, so 235 is base 10 into base 6. Okay, and that's the first example. So before we do this, just a wee bit of information. If I'm working in base 6, all the digits have to be either 0, 1, 2, 3, or 4, 5. Okay, that's how base 6 works. Okay, so base 10, if you actually think of any number we write down, that's any number, any digit is all between 0 and 9. Okay, so that's sort of how it works. Okay, but that's how we do it. So we're going to use the Euclidean algorithm to do this. Okay, so using the Euclidean algorithm, okay, we're going to start the process. Okay, so we're going to start off with a number that we're trying to change, 235. Now I want to change this number into base 6, so I'm going to be always thinking about how many times 6 can fit into this number. Okay, so it's going to be 6 times something, okay, then plus a remainder if there's any remainders there. Okay, so if I have a remainder, if I work out how many times 6 fits into 235, it fits in 39 times. Okay, and I have the remainder 1. Okay. Now, normally if you could do an algorithm, I'd move the 39 across and I'd move the remainder across. Okay. Well, I don't need to worry about the remainder part. It's just the amount that went into it. The 6 will actually always stay because it's always the 6 I want to deal with how many times in. Okay. So that 39 will go across. So it's going to be 39 will equal 6. Okay. And how many 6s will fit into 39? Well, it's going to be 6 6s. And my remainder here would be 3. Okay, so I didn't move the 1 across, it was just the 39 I moved over. That was my quotient. Okay, right, we're then going to move that 6 across. Okay, so 6 fits into 6, well, exactly once, with no remainder. Okay, now, normally when we do the Euclidean algorithm, we stop when we have no remainder. But that's when we normally find the greatest common divisor. That's not what we're doing here. What we're doing is we're going to continue until we can fit no more 6s into the previous number. Okay, so therefore that 1 will move across, but we can't fit 6 into 1 at all. Okay, I'll give myself a bit more space here. Okay, and I'd have a remainder 1 there. Okay, so I can't fit any more 6s in there, so I stop now at this bit here. Okay, so because the 0's there, I stop. Alright, therefore 235 into base 10, what you do is you read your remainders. Okay, so what my remainders are, but the key is you read it backwards. Okay, so you read it going that way. Okay, so we're going to read remainders backwards. Okay, therefore my number would be 1031 in base 6. Okay, that's what 235 would be written like in base 6. Okay, so a couple of key things to notice. Okay, you stop when you can fit no more of the base you're trying to fit into it, and also you read your remainders going in backwards order, okay, to get it. You okay with that as a first example? Right, okay, I'll show the second one. Okay. So example 2, express 423 in base 10 in base 8. Okay, so we're going to fit, we're going to try and change 423 normal structure base 10 into base 8. Okay, so starting off 423, well, how many 8s can we fit into 423? Well, it turns out we can fit 52 lots of 8 into 423 with 7 remainder. Okay, bring that 52 across, so 52, how many 8s can we fit into 52? We can fit 6 lots of 8 into 52, plus a remainder 4. Okay, and then we bring that 6 across. How many 8s fit into 6? Well, we can't fit any 8s into 6, so this will be the last step. And I would have 6 left over. Okay, so again, reading the numbers, going that way from the remainders, what that's telling me is that 423 in base 10 is 647 in base 8. Okay, you alright with that, folks? Alright, so there's a couple of examples of how you can change for a normal number in our structure using a sort of version of the Euclidean algorithm, not the whole thing, but a version of it, and changing it into different bases. You okay with that? Right, okay, we'll now look to see how we can express other bases back into base 10. Okay, we're going to look at the reverse process now. So expressing other bases into base 10. Okay. Alright, so again, we're going to start off just with an example. So we're going to, example 3, express 1234 in base 7 in base 10. Okay, so before I go to my solution, just a quick recap of what we discussed is that base 10, well, if something's in base 10, so our normal numbers, how it works is our units is 10 to the power 0, our tens columns 10 to the power 1, hundreds columns 10 to the power 2, squared, sorry, and our thousands would be 10 to the power 3, and so on. Okay, so we're going to use that information, but when it's in other bases, well, it looks similar. It would just be, for example, in the first one here, the first digit, so the 4, what we're talking about, okay, would be the sort of units version of base 7. So it'd be 7 to the power 0 in there. Okay, then it'd be 7 to the power 1, the next column would be 7 squared and 7 cubed, that sort of thing. Okay, so we're actually going to use that. Okay, so that's just a bit of info about base 10. Okay, because how we change from base 7 to base 10, well, because that's in base 7, well, it means that that 1, 2, 4, base 7, that 1 means that it's one lot of 7 cubed. Okay, because it's in the, what would be the equivalent of like the thousands column, okay, but it's in base 7, so it'd be 7 to the power 3 as opposed to 10 to the power 3. Okay, My next digit is 2, so it'll be plus 2 lots of 7 squared, plus 3 lots of 7 to the power 1, should say, plus 4 lots of 7 to the power 0. Okay, and what that gives me, if I work that out, you could just put all that in a calculator, you would end up with 466, which places it back in base 10. Okay, that's what that would become in base 10. Okay with that one? Alright, so you can actually see it's actually a bit quicker going from a different base into back into base 10, isn't it? Okay, give me a second example just so you've got a second one. There, example 4. Okay, so we're going to express, it's a bit bigger this one, so it's 223,000 I should say, 421 in base 5 into base 10. Okay, so solution. Okay, so we're dealing in powers of 5 now. Okay, so therefore the 1 will be hit with 5 power 0. That second, the 2 and the after before the 1 would be hitting up against a 5 to the power 1. So therefore what that means is that first 2 that we write down is actually going to be hitting 5 to the power 5. Okay. Plus 2 lots of 5 to the power 4, plus 3 lots of 5 to the power 3, plus 4 lots of 5 squared, 2 lots of 5 to the power 1, plus 1 lot of 5 to the power 0. Okay, and what that would give us is 7,985, which means we're now back in base 10. Okay, so you're just using the number that what base it's in to get it changed back from base, whatever it is, down to base 10. You okay with that one? Okay, I've just got one last wee one to show you, which I'll show you the process to it. So we'll just write changing bases now. Okay, wee subheading. So basically you can change a number from one base to any other base. Okay. So example 5. Express (2,213), which will be in base 4, if we want to change that into base 5. Okay. So how we do a question like this is what we do is we change it into base 10 first, and then we put it back into base 5. Okay, there's not a unique way to go from 45 in one sort of step. Okay, so if we changed into base 10 first, that would be 2 lots of 4 cubed plus, it's in base 4, 2 lots of 4 squared plus 1 lot of 4 to the power 1 plus 3 lots of 4 to the power 0. Okay, and what that would give me is that would give me 167 in base 10. Okay, so that's how you quickly change it in base 4 into base 10. Right, we're in base 10, I want to put this back into base 5, so that's when I use the Euclidean algorithm. So I'm changing to base 5. So I'm working out how many 5s fit into each number now, so it's 167, that'll be 5 times, well 5 fits into 167 33 times, with 2 as a remainder. Okay, so I'll bring the 33 over, 33 fits into 5 6 times, with a remainder of not 2, let's try that again, the remainder 3. Okay, 6 over, 6 fits into 5, sorry 5 fits into 6 one time, plus 1 remainder, bring that 1 over, 5 fits into 1 0 times, with a remainder 1. Remember, reading our numbers from our remainders in reverse order and backwards order. Therefore, 2213 in base 4 actually becomes 1132 in base 5. Okay with that?